Hi everyone, this video will walk you through lesson 8.2, the graphs of tangent functions. One thing that might be helpful for at least a small portion of this here is I'm going to reference that yellow value card that you have with all the different tangent function values. So if you want to have that handy while we're going through this here to plot some of these initial graphs, that might be kind of helpful. So similar to what we did with sine and cosine functions, we're going to look at some of our quote-unquote key points to create the basic parent function of tangent of x and create that graph. And then we're going to take a look at some basic transformations similar to what we did in lesson 8.1, where we're going to see some shifting, some stretching, etc. So let's take a look here at the graph of tangent of x. So this is going to look a little bit different from sine and cosine, mainly because there are certain values that with tangent do not exist. They are undefined, which means the graph is going to look a little bit different, like some of our other functions have that have had undefined values at different parts of the year. So when you take a look at your value card here, if I'm just looking from 0 to 2 pi, how to plot my different values here, what I'm going to take a look at here are some key values that ultimately will allow me to plot this. So if I look at, let's say, from a perspective of what's undefined and what's not, there's a couple of undefined values from 0 to 2 pi. Specifically, at pi over 2, the tangent of pi over 2 is undefined, and at 3 pi over 2, the tangent is undefined. What that means is that those undefined values, I'm going to have asymptotes. So I'm going to draw those into the graph, okay? And what that means is we'll see kind of the same thing on the other side of the graph as well, okay? Because as we know with our sine and cosine graphs, these are going to kind of repeat in perpetuity forever and ever and ever. So with our tangent graph, we're going to see a lot of the same thing. We're going to have a repeated pattern. It's just a matter of it's going to look a little bit different. Now, I'm going to focus primarily on what I just highlighted here in blue, this section of the graph, to kind of get my pattern, my cycle of the graph, and then we'll be able to mimic it in all the other gaps that we have here. So if I look at some of the other values, as you can remember here, with our graph, we're technically counting by pi over 4. We're just not labeling every pi over 4. So pi over 2 had an undefined value. If I take a look at our next most logical point to graph here, 3 pi over 4, the value of that is at -1. So I'm going to go ahead and plot that point. At 3 pi over, when tangent of 3 pi over 4 exists, we have a value of -1. At tangent of pi, we have 0. And at tangent of 5 pi over 4, we have a +1. Obviously, we have a couple values in between that would work. Now, when you look at this graph here, do not connect this as a straight diagonal line here. Okay, it's going to have a little bit of a bend to it because it's going to approach these asymptotes. So from pi over 2 to 3 pi over 2, you'll have a tangent graph that'll look as you see here. Now, I'm going to be able to mimic that in these other portions as well, in between the other sets of asymptotes. And they kind of look like those cubic graphs that we saw earlier in the year. But this is what a tangent graph will look like, okay? And then from there, we're going to talk about how to shift it around, how to stretch it, etc. So let's apply a couple of newer terms that we talked about the other day here with 8.1, the period and the amplitude. When we talk about period again references how long it takes for a full cycle of that graph to exist before the pattern repeats itself again. So the fact is we had from pi over 2 to 3 pi over 2, that's when we had one full cycle of this particular graph. And then for every other gap, it was the same length of time in order to get that particular cycle. So if I look at it from pi over 2 to 3 pi over 2, the distance between those two x values there is pi. So my period for a standard tangent graph is pi. It takes pi amount of distance, pi amount of time to complete that cycle. Amplitude you might remember as the height. Now, because this is not a sine and cosine graph, sine and cosine just kept going up and down and up and down, and it had all these peaks and valleys, but they clearly had a high point and a low point. In a tangent graph, it goes down forever, it goes up forever. The range on these graphs happen to be limitless. What that means is there is no amplitude. There is no defined height because I can't measure from the middle to the top or the middle to the bottom because they go on infinitely. So for tangent, we're not going to talk about amplitude because it's not applicable. There is no defined height with a tangent graph. So, period, that cycle of time to complete the pattern, it takes the amount of pi. Amplitude doesn't exist because it's undefined. So we're going to keep that in mind here as we look at some manipulations and some transformations of these graphs. Again, we're going to look at, small amounts of these here, and then you'll practice these here with a couple of problems that I'll assign with this here. So here I have, it's the same tangent graph. You'll notice it kind of looks a little bit wider than the graph that I have up above, mainly because if you notice the scale, this one actually has every 2 lines counting as pi over 4 versus every line being pi over 4, like the blank graphs that I have. Why that scale is a little bit different here, I guess these are the images that I just found here, but that's just something to keep in mind why you might be looking and saying why it's a little bit different. These graphs here at the end, okay, those are also supposed to mimic the next wave of the tangent function with, from the left and the right side here. If you're wondering what those arrows in the corners mean, it's still the same graph, just very, very compressed for some reason. But at any rate here, what you see here for number 2, this is tangent of x. The one thing that's going to be different here is I want to graph 2 times the tangent of x. We talked about in 8.1, if you have a value in the very, very front, that is going to affect, when it was sine and cosine, that affected the amplitude. Well, we don't have an amplitude in this case, but we can apply something kind of similar to this here. Whenever you have a number out in front, you can affect the vertical stretch or shrink of the graph. Because I have a value that's greater than 1, and the absolute value of it greater than 1, we are going to have a vertical stretch of all of our key points on the graph. So, what does that look like? I can go to any of these portions here. I'll just start with the one that's here on the left side here. If I'm on the x-axis, I'm not able to stretch vertically because a vertical stretch of a y value of 0 still ends up being 0. I'm going to take these couple of key points that I have circled, okay? They have y values of -1 and 1. Because my vertical stretch is of 2, I'm just going to double those values. So my -1 will get doubled to -2. My +1 will get doubled to +2. So it's going to take my graph, and as you can visually see there, it stretches it out. And what's nice about that is, again, once I do it for 1, I'm going to go ahead and do it for the others. And admittedly, I'm cheating a little bit by copying and pasting. But every part of my tangent graph will look exactly like that, where I'm just taking the key critical points and I'm doubling their y values. That's what a vertical stretch would do. So that's how you would work with a problem like number 2. Tangent of x, 2 times that, it's just going to stretch that graph out vertically. There's a few more examples here on the next page. These next couple are also going to deal with vertical stretching as well. So in number 3, it's 1/4 the tangent of x. Well, by definition, okay, 1/4, I'm not stretching it in this case, okay? Technically, this is what would be called a vertical shrink or a compression, depending on what word you want to use there, okay? So I'm going to do the same thing I did before. Again, my point that has a y value of 0 is going to stay put. I'm going to take my other 2 key points, and I'm going to, again, cut them by 1/4, okay? I'm going to take 1/4 of them. So I'm going to end up shrinking and compressing, kind of squashing the graph a little bit here. So where I had -1, I'm going to eyeball where roughly -1/4 would be. And +1, I'm going to eyeball where +1/4 would be. So it's not going to be, flat, but it's going to be pretty close to it. So it's not the most perfect graph here, but that'll do. Okay, and then I'm going to do the same thing here for my other parts of the graph here and show that same vertical shrink. In number 4, once again, we have another value that's a multiplier to that tangent of x, so we're going to be doing some vertical stretching / shrinking. What's different about it, though? There's a negative sign. And we saw one of these here with our sine and cosine graphs the other day. If we have a negative sign out front, not only could we possibly be stretching or shrinking, but that negative sign says we are going to reflect over the x-axis. So I'm going to take all my critical points, I'm going to reflect them over the x-axis, but not only am I going to do that, the fact that I've got the number of 3 means I've got a vertical stretch. So I'm going to reflect my point and then triple that y value. So for example here, so again, beauty of being at 0, that's going to stay put. If I take my key point of negative 5 over 4, at negative 5 pi over 4, that y value of negative 1, if I reflect it, I'd be at positive 1, and then I'm going to triple it all the way up to 3. Same thing with my critical value there, negative 3 pi over 4, the y value of 1. I'm going to reflect it down to negative 1, and then triple that and get it to negative 3. So I'll make those a little bit smaller here. So it's going to have a lot more of a vertical look to it. Again, it's not a straight line. It is going to curve. And then all we're going to do here is mimic that in all the other portions of the graph. So that's some good examples there of some vertical stretching, some vertical shrinking. We also have the reflection over the x-axis there with that negative out in front. It's a very common manipulation you'll see with these graphs. Let's talk about one other part here that we did talk about with sine and cosine the other day, where we talk about the horizontal stretching or shrinking. And as you can see here with 5 and 6, my number is not out in the front. Okay, my number is directly associated as a multiplier to the x value. So when I have a number that's directly being multiplied to the x value, to my angle, that is going to tell me I need to shrink or stretch my graph horizontally rather than vertically. And we know from horizontal and stuff related to x with our transformations, that can be a little bit trickier because, again, we have to think the opposite way. So if I'm looking at something like the tangent of 2x, so I'm going to look at all my key points as well as my asymptotes, because my asymptotes are going to actually be moving in and out horizontally as well. With these particular values here, okay, if I have something like 2x, what I want to take a look at here is I want to figure out what my new period would be. So remember from sine and cosine, we had the original period, and whatever the value was that was being multiplied to the x, we would divide it away to figure out what the new period of that particular graph would be. In this particular case, because it's tangent, my initial period is pi. I'm going to divide away what's being multiplied to the x here, which in this case is 2. Now, pi over 2 doesn't go anywhere. The period of each of these segments of the portions of the graph here, it'll take pi over 2 as a distance to ultimately complete the entire cycle. What that means is these graphs are going to be horizontally shrunk or compressed. And I'm going to be able to complete these quick little curves here in half the time. So how do I show that? So again, if I'm at 0, I'm going to start here from the middle because I think that'll be the easiest with horizontal. Start at 0. Okay, obviously I'm not going to be able to, if I try to divide 0 in half here, that's not going to do anything. But I'm going to take my couple of key points. So right here, negative pi over 4 comma negative 1 and pi over 4 comma 1. Because I'm cutting the period in half, I want to take them and move them in by half. So I'm going to move those points in. And again, I'm going to make those a little bit smaller. The other thing I'm going to do, so I have these asymptote lines, and I know they're not dotted on this diagram for some reason, okay? But those asymptotes, because the period is being done in half the time, that means my asymptotes are going to be halfway in as well. So I'm going to go from negative pi over 2 in half, and from pi over 2 in half. So it's going to make it a lot smaller of a window here. But this would be one complete cycle of the tangent of 2x. Once I have this in to fill the rest of the graph, I'm just copying and pasting this the whole way across. So as you can see here, I'm just, now I can, easily do this here with technology. But all I'm going to do is take that same window here, because it's only being done in half the time, and I'm just going to go the whole way across with it as far as I humanly can. And eventually here I do run out of graph, but you can see I can just continue to extend it forever and ever and ever. And then I can go on the opposite side of it here. And there's my graph. Okay? So when you have something like tangent of 2x, it's taking the time it needs to complete the entire cycle of the graph, it cuts it in half. So again, it's the opposite of what you think. You see that multiplier of 2, it's really cutting it in half. Number 6, it's kind of the same idea. Has a multiplier of 1/2 directly with the x. In terms of figuring out what the period of that would be, I'm going to do the same thing we did before. My original period for a tangent graph is pi. I'm going to divide by the 1/2. So when you see a multiplier that's under 1, okay, between 0 and 1, it's actually going to extend the period. It's going to make it a longer cycle to complete one full pattern of this graph. So in this particular case, it'll take pi divided by 1/2 comes out to 2 pi. It'll take a distance, a length of 2 pi to complete the entirety of the cycle. So if I look at this here, this will essentially come out to a horizontal stretch, because it's going to take longer for it to complete. So I'm going to start again at dead center. And I've got my couple of key points here that I'm going to put on the graph. And we have our asymptotes here. Again, this is all the original graph. I'm just drawing this here so you can see me actually physically moving these things. Because it's going to take double the period length, that means those asymptotes are going to be double the period length. So I'm going to go from negative pi over 2 to pi, because that's double, and pi over 2 to pi, because that's double. That also means my couple of critical points here. The one in the dead center at 0, 0, that'll stay put, because doubling 0 doesn't do anything. Horizontally, if I'm at negative pi over 4, double gets me to negative pi over 2. And pi over 4 doubled gets me to pi over 2. So it's going to elongate that central part of the graph there. Still going to make this big curve here, but it's just going to be extended out. And I can continue that pattern with both the left and the right sides of the graph. It might be a little bit harder to see them extended out, but you would be able to have a graph that's kind of going in this general direction here on the left side. And then on the right here, again, you can see I can kind of start the pattern this way and then work my way up. So there you have some examples here of the tangent graph, okay, some of the key properties of it, mainly with the period, and again, our discussion briefly there with amplitude, but also some of the ways that we can transform and manipulate that graph. So that's your information here about how to graph a tangent function. for your assignment with this here, there is a Word document posted here. Well, it's PDF, but there is a homework document posted. It's 3 graphs that I would like you to try and work through. If you have any questions with this, please let me know. Please do give these a try, because we are going to move on the next day here with what we call the reciprocal functions. So you need to have some knowledge on how to do this here. So give these a try. Let me know if I can help you with anything. Otherwise, have a great day.